Hi friends, let's have a look at problem 3228, maximum number of operations to move ones to the end. This is a very interesting problem and it's frequently asked in interviews. So here we are going to provide a solution that is space and time are both O of n, in other words, linear time and linear space. But it's very straightforward to transform it to be a linear time solution and a constant space solution, right? So here we are given a binary string. In other words, the S consists of zeros and ones. So we can perform the following operations on the string any number of times. So we can choose any index I from the string where I is in bound, right? And such that Si is 1 and Si plus 1 is 0, right? And then we move the character Si to the right until it reaches the end of the string or another 1. And for example here, because here we have 1, 0, right? So we can move this 1 up to this 0 because we meet another 1, right? So we get 0, 0, 0, 1 and 1, 0. So we want to return the maximum number of operations we can perform. So here we have two examples. So example 2 is very special because all the ones are in the tail. So we need so we don't need to do any move or transformations. So we are going to use example 1 to fix the idea. So before we do the analysis, let me first tell you or share with you the reduction of the problem. So this problem actually reduces to a simple summation problem. So more precisely, so it's very cool. For example, we have the following array. So here we have A1, A2, A3. Then its partial sum will be A1, right? This is the first item. The second item will be the sum of the first two terms, that is A1 plus A2. And the third term is the summation of the first three terms, and so on. So this is the so-called partial sum array. Some people also call it prefix sum, but in mathematics, so this partial sum array is more precise. Then we want to compute the sum of the partial sum. So in other words, the summation is this one and this one and this one and this one. But if you do the counting, you know A1 is count 4 times, and A2 is count A1 is count for 4 times, right? And A2 is counted for 3 times, and A3 2 times, and A4 1 time. So you have something like this. So this is the sum of partial sum. So in general term, it's like something like this: n A1, n minus 1 A2, and 1 times an. Notice here I'm using 1 indexing, but transforming from 1 indexing to 0 index is sort of trivial. So here I want to make a connection with this problem. So here we have this one. This is the S in example 1. So we want there are two options to move ones to the right. So first we notice that the tailing ones do not play any role, right? So we can just drop all those ones. So here, this one. So we can remove this one and we interpret S as 1, 0, 0, 1, 1, 0. So notice that we cannot delete this 0 because this determines if we can do the move, right? Because only we have 1, 0, we can move the ones to the right until to the end or meet another one, right? So here, there are two ways to do the move. The first option is that we move from right to left. So here we have 1, 0, right? So we move the 1 to the right. So we get 0, 1, right? Then we still move from right to left. So here we have 1, 0 again. So we sort of change the order. So we get 1, 0, 0. So then we have 0, 1, 1, right? This is another step. Then here we have 1, 0 again, right? We put this 1 in front of the this one. So we get 0, 0, 3 zeros, 3 ones. So this needs 3 steps. So in other words, we just need to count the consecutive ones separated by zeros, right? So here, we have 1, and here we have 2. Then we get 1 plus 2, that is 3. So this operation, this way we do the operation from right to left, and we can also do from left to right. For example, here we have 1 0, right? So we can first move this one to the second one. So we get 0 0 1 1 1, right? And that's 0. So this way we move the first block of 1s to the second block of 1s. Then together they will have 3 1s, right? Then we want to move the 3 1s to the tail. So here we have 1 0, right? So we move to here, another step, and here we have 1 0 again. So we move to 0 1 1, then another 1. So we get 0 0 0 and 1 1. So this needs 4 steps. So we want to notice the difference of this one from the first one. So notice that it amounts to first accumulate from left, then move to the next blocks of 1s, and finally move the full block of 1s to the end. So here actually we have block size 1s of block size say 1 and 2, right? So we first move the blocks of size 1 to the next block. So we get so that we need 1 step, and now we have the 1s of block size 1 plus 2, that is 3. Then 1 plus this 3, we get a 4, right? So to sum up, so option 1 is to compute the sum of the block sizes of consecutive 1s, while option 2 is to compute, so let's change this one, compute the sum of the partial sums of block sizes. So let me emphasize again. So here we have block of 1s separated by 0 like this, right? So of course we delete the tail ones. Then first we gather, we compute the partial sums. So we get 1 and 3, and then we compute the partial sums, the sum of partial sums, that is 4. So that's the problem. That's also why we, at the very beginning, we reduce the problem to a simple summation problem. But here, what we want to sum is nothing but the partial sums, right? So if we want to see what's the minimum number of operations we can perform to make it all the ones to tail, so that will be the partial sums, not partial sums, the sum of the sizes of one's blocks, right? So now with this said, so solving the problem will be rather straightforward. So let's look at the code. We want to do 2 things. First, we want to trim all the tailing zeros, right? So this will be rather straightforward. Here I can do something like this. Let me introduce this length n. This is the length of s. So we can use a pointer method, right? We use the red pointer point to the last index. So here we want to do a while loop while r is greater than or equal to 0. In other words, r is a valid index, and sr equals, so here is string, this equals 1, right? Then we're going to move one step to the left, right? So afterwards, so this r is either a -1, it means that all the strings consist of 1s, or it stops at a index which is corresponding to a 0, right? Then we want to identify the s to be that string. In other words, the s without the tailing zeros. So this is the string, right? Notice here we write r plus 1. You can think of r equals -1, right? We cannot up to -1, so we get r 0, right? So you can use this one to understand. For example, here 0, 1, 2, 3, 4, 5, and 6. So you are going to get 5, but you need to do the slicing, writing 6 here to get this string. So with that done, now let's look at we find the segments of ones. So this can be easily done, right? So find the segments of consecutive ones. This can be easily done. This can be easily done by the split function or method of string. So what we mean is that we want to do split So this will give us with split at 0, but because it's some consecutive zeros, we're going to have some empty strings. Let's print out this one to give you an idea, right? Let's see, did I print? Let's see. So here we need to write, this is a separator, right? So you see here, because there are some, this corresponds to zeros, right? So then we just need to do a list comprehension to filter out those empty ones. So this can be very straightforward. Let me write some additional steps so that the idea is clear. So we get segments of ones. So it'll be something like this. So what we want to do is we want to pick those items for atom in this one, because this gives us a list, right? We want to find this non-empty list. So if atom, right? So this will give you this one, this blocks. Let's print out those. You can do something like this. Right, so you get 1 and 1, but what we want to do is the size. But the size is nothing but the length of this each strings, right? So we can do say segments length. So this is also a list comprehension. Length atom for atom in here. So you will get this one. Let's also print out this so that you follow the procedure. So this corresponds to 1, 2, right? So then you can do the computation, right? So for doing the computation, you can first compute the partial sum and then just use the sum built-in function. So this is the one way. But you can also do like here, right? So here, the first term is multiplied, counted n times. N is the length, right? The second term is counted n minus 1 times. The last atom count 1 time. So we can use that one. So let's see. We want to return. So here, summation. I'm going to use this one. So here, n minus I times length for I length in enumerate segment length. So we can use a default value that is 0, right? So here you see, if I equals 0, it corresponds to the first term in the length, right? So we want to multiply this term n times, where n is the length of this segment length, right? So then the second term corresponding to index 1. So if I equals 1, it is n minus 1, right? Counting n minus 1 times. So this is exactly what we need. So let's do a test. Segment length is not segments. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the cases, but this is a relatively fast way. But if you want to say do it slightly different, you don't need to. If you don't know this formula in the return, so you can do something like this. So let me change this one to be version v1, right? So when we get this segment length, so what we do, we can do something like this. So we can first get the partial sums. So, but this will need another for loop. So for I in range, so 1 to length. Let's copy this to avoid typing errors. So we get this, and then what we want to do is segments length I is incremented by the previous one, right? So this way we get the partial sum. Then we just need to return sum of this guy. This is actually the same thing, but this one is faster. Let's test that. So this is the one comment. Another comment is on the time and space time complexity. So here in these two versions of solution, so I'm using this one. Let's use this one as a sort of let's see, v, just as a v. Here the time complexity will be linear, right? It's O of n. So here space is also O of n. But notice that what matters for this problem is nothing but the consecutive one's length, right? So we can easily get the block size, and in between, when we do the for loop, so we can accumulate this partial sums. In other words, we can use a time On and space O1 solution. So here a follow-up might be this. Improve the solution to be a time On and space O1 solution. This will be a very interesting practice. So actually, I give some post in LeetCode, so which I shared two versions of solution. One version is this one, which is both time and space are O of n. And also we improve it to be space O1. You can have a try. But here, the first version here is sufficient to fix the idea and explain the logic. With that said, I guess that's it for the current problem.